Welcome, everybody. Thank you for coming to this event jointly hosted by the Center for Global Energy Policy and the Earth Institute. If you haven't met me before, my name is Julio Friedmann. I'm a senior research scholar here at the Center for Global Energy Policy and delighted to have you all here with us today, among other things, sharing some time with redoubtable and remarkable David Keith. David is somebody who I've known for a very long time. We met originally in 2003. We met over a pint in Cambridge University, and it's been trouble ever since. David is one of the most prolific and one of the most insightful and one of the most accomplished scientists of his generation. He is the only person I know who has a joint appointment in a school of engineering and applied science as well as a school for public policy. And some little chump university in Cambridge, I can't remember what it's called. But he made a couple of really important, straightforward arithmetic calculations a few years ago in which he looked at what we were trying to do on climate. And for those of you who don't know his full story, he actually started in climate modeling many, many years ago. And basically did some arithmetic and said, there's two things we don't have that we will need. We're going to overshoot, so we need to figure out a way to remove carbon dioxide from the atmosphere. And we're going to overshoot, so we should think seriously about solar radiation management and geoengineering. And he went and wrote a couple of papers on those topics and then started a company that pulls CO2 from the atmosphere and started a research program to look at solar radiation management. I could spend a lot more time talking about how much fun it is to spend time with David, but you'll figure that out yourselves. With that, please help me welcome Dr. David Keith.
Thanks very much. Thank you. Thanks a lot. It's a really pleasure to be here. I'm going to try and do too much, and so bear with me because I'm going to try and fit it together in a way that's a little awkward. So that was a great introduction, but actually it's not quite right in the sense that I didn't start by thinking we need air capture, and I really don't think that quite as much maybe as you and some others do. I started for air capture by thinking that people were overclaiming about it and that it was important to understand what it cost. I love Klaus, but I thought he was overclaiming a little bit, and we thought it was really important to assess the costs, and that's where that grew out of. And I actually had a long background doing climate science and originally physics before that. I think it's important to say that I'm talking about two things that are really different in my relationship to them and the way they fit in the climate policy space. So I'm going to spend most of my time talking about carbon engineering's direct air capture process and how we've developed it, then talk about what I see as one of its most important applications, or more broadly, one of the most important applications of direct air capture in general, which is enabling low carbon fuels from cheap renewable power, solar power. And then third, I'm going to very briefly give a talk that normally is part of a talk on my main day job, which is on solar geoengineering, talking about how all these instruments, emissions cuts or mitigation, carbon removal, solar geoengineering, and adaptation might fit together in optimal climate policy over time. But it's important to say that I have very different affiliations and ways of working on these problems. So in carbon engineering as a company, I was the founder, but since the time that I founded it, I've stopped doing any academic work on that topic to kind of avoid conflicts of interest. Indeed, I don't have any academic work in energy anymore. So I really want to divide the two things up. I love the work we're doing in carbon engineering, but it's a pretty small fraction of my time, like 10 or 15%. So my main work is really on solar geoengineering and its technology and policy. I won't be talking much about that, but I'm really happy to take questions about it. Without further ado, I want to go very quickly through the kind of core argument behind the development of the direct air capture process of carbon engineering. Happy to take more technical questions later, but this will go pretty fast. From the beginning, this company and the research program before it was built around trying to find low cost, low capital cost, and low technical risk pathways to air capture. We had for a while a sign that I made in the Office of Carbon Engineering that said no science. The idea is that if you want to develop something that you can credibly bring to market at the million-ton-a-year scale pretty quickly, you have to mostly build it closely on the back of industrial technologies that you can go work with existing vendors and build. Not 100%, but that was the core idea. So we were not trying to develop some magic new laboratory thing. We were trying to apply kind of blue-collar, classic chemical and mechanical engineering to solve a problem, building as much as possible on existing tools. That was carbon engineering from the beginning, and it still is. This gives you some little sense of the kind of iterative way we've been doing hardware. So we started to build a significant scale hardware back in '05 before the company was founded in '09. And as is true for lots of hardware development projects, that's not just us, but a lot of that is with suppliers. So, for example, this 2013 calciner test picture was with a company that does high temperature materials processing for their minerals and mining industry in Golden, Colorado. And they did a whole bunch of work for us and maybe doing some again now. So the core of the carbon engineering process is this 2-chemical loop process where the first loop is an aqueous process that takes carbon dioxide from the atmosphere using a strong base, potassium or sodium hydroxide, mostly potassium. And the things we like about that are, first of all, that it's not volatile. So amines in some ways are superior, but amines and many other things like them you would lose to the atmosphere. That both turns out to cause significant air pollution problems, and you'd be losing money through the amount you paid for them. So the good thing about these strong inorganic bases is that they have fast mass transfer, which you must have, and that they're sort of simple chemicals that existing industrial enterprises can handle. So the core of the technology I'll spend the most time talking about is the air contactor. And we think that's really the platform of our technology. That's the thing that we can build on using different backends we think, enable the cheapest path to really large-scale air capture. I'll come back to why I think that's true. This core 2-loop process is borrowed very closely from the way pulp and paper works. So all of you, most of the paper that you hold comes from pulp and paper processes that use kind of the same 2-chemical loops. So in pulp and paper, you use sodium hydroxide, putting it on the wood to break up the lignin that makes aqueous sodium carbonate. But you couldn't make economic paper that way. You have to recover the sodium hydroxide. And this loop here in the paper industry lingo is called a caustic recovery loop. And we spent a bunch of time working with the paper industry people, understanding their processes, working with the engineering, procurement, and construction firms that work with them to really build on that industrial heritage. What we do now is quite different, and the big difference seems kind of trivial, but it's really quite fundamental. The big difference is in this pellet reactor. It's exactly the same reaction as pulp and paper does, but in pulp and paper, people make this stuff called lime mud. It's about 5-micron average size calcium carbonate, which is the natural thing you get when you just mix those in a big vat. And that stuff is very hard to work with, hard to dewater, hard to dry the final bit. Has a lot of what we call alkali carryover. That is, alkali remains stuck to the material, so it's hard to manage in the high temperature kiln. And the thing we did is adapt some technology that existed for wastewater treatment at large scale. Various companies have it. We've been working with a company called DHV in the Netherlands that's built very large scale wastewater treatment on this technology. We adapted that, and what that does is instead of making these little, say, 5-micron calcium carbonate, it makes kind of nice, hard, low porosity, spherical, roughly half-millimeter pellets. And that turns out to just make everything on the other side easier. I'll get to that in a second. So this is just a high-level process flow diagram that's from this paper that we published in Joule. So in general, this is a company. Our business isn't to publish academic papers, but because there were really different views in the academic community that mattered to us about whether air capture was even possible or how it worked, we thought it was really worthwhile to publish something that was a complete energy and materials balance and to show a bunch of the industrial costing behind it. But it's important to say that, for those of you, obviously I'm not expecting you to read this right now, you can go look at the paper, but for those of you who may be kind of academics from outside chemical engineering who look at this might look complicated. This is actually a very, very simple version of the real process flow diagram currently being developed at Carbon Engineering. So we're now just on one process right at the end of what's called FEL3, front-end loading 3, of a big engineering, procurement, and construction process for a big step up in size. And for the million-ton-a-year plant, we're in the beginning of that EPC process. And if you actually came and could look at all the things that are sitting on our engineer's desk, there's lots of complexity. So when you see some silly little pump there, in reality, that may be quite a few different pumps with different specifications that do different things. And that's true in almost every one of these pieces. So this is the reality of a technology like this, is it's complex, and that has profound implications for its scaling. So we think we are very cheap when we're big, but if you wanted to use a process like this to capture a kiloton of CO2 from the atmosphere a year, the cost would basically be infinity because all these individual elements cost a lot. This particular design, just because there's been really kind of controversy about air capture, this particular design takes only natural gas as input. So we decided to make it electrically neutral. We don't think we ever build a plant like that. It was just a convenience for a paper because people had questions about how to think about the total balance. So in this design, it's electrically neutral, only gas in, and basically in this particular version, it's making high pressure CO2 that you'd want for DAC sequestration, which is only one of the applications of DAC. So it's making 150 bar CO2. And in that application, for every ton of CO2 you capture from the atmosphere, you burn enough natural gas to make about an extra 0.45 tons. You're capturing all that natural gas, the leakage is minuscule, and you are compressing it as well. So you're delivering about 1.45 tons of compressed product for every ton you got from the atmosphere. But that's in this configuration that in general is not one we think we're using that much. So let me just spend a little bit more time talking most importantly about the contactor, so that these little blue areas show the areas that I'm talking about in the process flow. So this is really the heart of it. If you want to capture CO2 from the atmosphere, you have to make the capital and operating cost of the thing that first does the capture low, or you're doomed. And let me give you some numbers to sort of back that up. It turns out that when you look at our process or the competitors' processes, you pretty quickly find that you're somewhere around 10 tons of CO2 per square meter of inlet area per year. There are some trade-offs that get you there, because you've got a trade-off where you can choose how fast the fans are blowing. You could just allow the wind to carry the CO2 in, but then when there isn't wind, you're still paying the bank. It's really an inefficient thing to do, so you almost certainly want to be blowing air through it. There's a trade-off about velocity. There's trade-offs about how much you capture, but you typically keep coming to a number like that. So if you can only get 10 tons per square meter of inlet, that can sort of tell you directly how much you can afford to pay for a square meter of inlet. So, for example, if it was $3,000 a square meter and you had 10% overall capital recovery factor, including O&M, which is kind of reasonable industrial number, then that's $300 sort of rental, if you like, for every square meter. So that's $30 a ton just for that process. So you could, maybe afford to be higher, but it's something like that. So in our view, that applies to any of these systems. And remember, air is not laboratory air. It contains contaminants, it contains insects, it contains dust, and this thing has to operate for decades cheaply. So our view is that building an aqueous process allows operation all the time. It naturally, and in a proven way, allows cleaning of contaminants, because these processes we're building on top, these forced draft air cooling towers used all over the world, have been developed for more than half a century now to withstand contaminants. It turns out that they have been developed, many of them, to withstand these strong hydroxide solutions, because they are used for biofouling, cleaning biofouling. So it turns out that they are almost every element of them are already compatible with these strong hydroxide solutions. Our actual contactor configuration, which no longer looks so much like the one in that picture, is different from the geometric configuration of forced draft cooling towers. But the key thing is we are relying on all the same hardware. So very similar packing. Packing is the corrugated material, corrugated plastic material where the fluid flows over it and the air blows through it. It's a contactor because you're bringing the air in contact with the fluid. And here's sort of the key number. Commercially, that stuff costs $1 per square meter installed. And you need to get costs that are of that order if you're going to make this work. And I think that's one of the challenges of the alternative way to do air capture, which is that you use some clever sorbent, some clever solid sorbent. That clever solid sorbent has to be the entire same size if you're going to capture the same amount of CO2. Then you have to cycle the entire thing, and you have to have that operate for a long time in the face of contaminants. I think both processes are important. We can talk more about it, but that's why we think the liquid one is so important. So we use the same packings, the same fiber-reinforced construction materials they're using, the same fans, a bunch of the same distribution panels. All that stuff we borrowed, but we use it in a slightly different configuration. And we've now built several generations of these things and run them for kind of 10,000 hour class time. So that's a kind of very high-level view about what this thing looks like. I'll go through the rest of this more quickly. So that's the pellet reactor. And again, I just want to emphasize industrial heritage of these things. So it's hard to see, but on the upper left, there's a pellet reactor being built with very similar technology in a Middle East location by DHV, and that is very similar to the kind of scale we want to build, and so we think we really understand the costs and operational details, and we've built our own pellet reactors that work under our conditions, several of them, and gives us a lot of industrial heritage. Calciner I'll skip through. So this is just the end of the kind of technical part. I know this isn't, some of you have chemie background, some not, but I wanted to just give you some idea of the underlying to background behind it. These are numbers from this published Joule paper, and people often in the kind of secondary literature, because obviously there's people who have strong chemical engineering background who really want to understand these processes, but then there's a lot of public policy discussion around carbon removal. And people have tended to take this paper and look at the highest and lowest number as a range. Of course, it's not a range. That was a sort of a trick I put in the paper to make sure that people would not focus on a single number, and it worked. What you actually have are several completely different configurations here that you should never be comparing. And it was interesting to see, like Jim Hansen wrote a really nice piece about this, and he's a careful reader. He got it. But there's uncountable versions of literature that didn't. So the top two are just two versions of the same thing I showed before, which I don't think we ever build with different financials. But the bottom two relate to really different configurations that are closer to what's likely to be built, but they're for different purposes. So the C configuration would assume that we use a significant amount of imported electricity, and then you got to think about what the life cycle carbon intensity of electricity is. It has to be relatively low. It doesn't have to be zero. And I think it's almost certain we do that. So when we actually think about what we're actually citing, we're looking at contracts where you can get solar and wind mixtures with very high availabilities and very low net carbon at low cost. So that's almost certainly what we do. And the last configuration, which is the one that I'll now talk about, is where if you want to make CO2 for fuels, you don't need to have super high pressure CO2. And also, if you're using this configuration, you don't need to pay for the oxygen because you've got an electrolysis process on the hydrogen that's making you free oxygen. So that saves you a bunch of money and energy. This is all assuming that you're using this natural gas-based process. To be clear, Carbon Engineering is already working on and piloting electricity, all electrical processes that use the same calcium loop, but electrically driven calcium loop. But there's also a series of things that don't involve the calcium loop and are not high temperature. So if you look at the patent that we call the CMETS patent that's out there, it gives you some idea of one of these processes that involves nanofiltration and electrochemical method, but there's a bunch more, and we're working with a bunch of academic groups to try and figure out alternatives to the calcium cycle. This gives you just some pictures of what things look like out there now. So next, I want to talk about what I see as one of the most important near-term applications of how our air capture technology, which is the one I know the best, but in general, I don't mean this to be specific to ours. To me, this is really an energy pathway that may be one of the major energy pathways over the next century. And I want to kind of defend why I think that might be true. And that pathway is this pathway of making carbon-neutral hydrocarbons. And to be clear, I think this competes with a bunch of other things, and there are lots of places, like short-duty vehicles in cities like this, where I am sure electric vehicles are going to win. And so I'm not thinking this takes over all of transportation. I'm thinking it takes over some niches. I think it's sort of easy to see why I might be skeptical about biofuels because of their environmental footprint. Hydrogen is in some ways terrific because it has such a high energy per unit mass. And so that gives you this potential giant benefit for using it for airplanes. But in all sorts of ways, it's a terrible fuel with low heating value. It's hard to compress. There are just a lot of reasons why you might want to do hydrogen, might not want to. And I think the big message here is if you've got CO2 from the air at a reasonable cost and you've got carbon neutral hydrogen, you might just want to combine them to make a fuel because then you have something that's easy to store and easy to transport. I don't think that'll be true everywhere. I think what we'll see is a more heterogeneous market where you will see more of these things, but I think it's important. So let's say I'm going to, for now, talk about going from, how you would go from solar photovoltaic, which is intermittent, to making some fuel, which is a storable, transportable fuel, a hydrocarbon which is drop-in compatible with existing uses. So aviation kerosene, so jet fuel, or diesel or gasoline. Why am I starting with solar? For reasons I'm happy to try and answer in questions, I think that solar is really one of the only two energy sources that are practically scalable to the tens of terawatts that a carbon neutral, high energy society would want without big energy footprints. I think it's really only solar and nuclear. There's nothing else that you can scale without having really large environmental footprints of some kind. And I'm also particularly excited because the costs of solar PV have dropped in extraordinary fashion. I know lots of you know that, but it is just amazing. And I feel it sharply myself because I feel I was clearly wrong. Like, we published 2 different analyses showing that in different ways that the solar learning curve was flattening out. We did a big expert elicitation exercise that showed that, we just might get to module costs of sort of under 30 cents a watt by 2030. We're basically there now. So it is really extraordinary what's happened. And my view is this is sort of a slow-moving but real game changer for the whole energy landscape. You can build these huge solar facilities. This is one that exists in North India that's over 2 gigawatts. Even a few years ago, I would have been amazed there was such a thing. You can already build these things at well under $1,000 a watt installed, and they have capacity factors up to 30%, and I think there's no reason to believe we're not going to grind that down to under $500 a watt pretty soon. I think that really changes the way you think about energy. It means that not everywhere, not in New York City, but in places that have really high insulation and relatively low land costs, you can basically make carbon-free energy at extraordinarily low costs. But that doesn't magically decarbonize the world, right? Because it's only there during the day, and it's only in some places. And the challenge is how to use that extraordinarily cheap low-carbon energy to do decarbonization. And where we can, we'll do it by running high-voltage lines or whatever, but there are other things we might want. And the general picture here is you might want to make a high-value, high-energy density thing that you co-locate with that. You've got to manage the intermittency, and then you move to demand centers. And that could be aluminum, roughly 1% of primary energy, or ammonia, or most of all, fuels. So quickly, how do you do it? You need direct air capture. The numbers I'm going to show you are for our process, which I've already showed you, but there's nothing that, I don't mean this to be parochial to carbon engineering. The next big thing you need is you need to do hydrogen electrolysis. And it is really exciting to see how the technology and market for hydrogen electrolysis is changing. Suddenly, there are deals floating around that are over 100 megawatts. We are talking partly, this is my non-academic work through carbon engineering, with companies like NELS under NDAs and with some Chinese companies. I like NELS because they play in both camps. They both make a PEM, a proton exchange membrane. This is like a kind of fuel cell electrolyzer, and they make the alkaline electrolyzers, so they see both, and we can really talk with them about both. But I am really convinced that the costs of these large electrolysis systems are going to fall pretty quickly. And this isn't hoping for some innovation that's just some learning curve. It's intimate knowledge of the way the construction costs and supply costs inside those companies work that they've given us. And I think the idea that you can get to something like $500 a kW for large electrolysis kind of in the mid-2020s is very real. So if you want to make fuel, you want to take water, electrolyze it to hydrogen, and I'm claiming that these costs here are really getting low and practical. This is all about how to do this. To be clear, this talk is about how to do this using existing or soon-to-exist technologies at industrial scale. For sure, there are clever ways to do this, artificial leaves or whatever, but that's above my pay grade. Then you have the question of how to make carbon monoxide. And we at Carbon Engineering, even 2 years ago, were looking a lot at reverse water gas shift, which is, we like these kind of blue-collar, dumb ways to do things. It works, but it's just not nice. And we always thought that it would be much nicer to have an electrolytic process, but we always thought that was off in the future and nobody could supply it. That has changed. So in the last year, Haldor Topsoe has brought this system to market, and they are a very respected, serious company. They don't do stuff like this casually. So this is only a 300 kilowatt unit, but they've got a lot of these in the field, and the specs of it are public. You can go look them up, and we think it's very realistic that Haldor could be building these things in the multi-megawatt pretty quickly. And these do with a high temperature solid oxide fuel cell core, they are electrolyzing CO2 to CO. And that's crucial to making this fly. So then you're going electrolyzing water to hydrogen, electrolyzing CO2 to CO. Then you got a mixture of hydrogen and CO. That's what you call syngas. Then you want to make fuels. That's the easy part. This is the Shell Pearl plant, which is 140,000 barrels a day. There's about 250,000 barrels a day globally. This is a technology people really understand. And these things, if you count from the syngas, forgetting how you got it, because of course In the real world today, these are used mostly from natural gas or coal. But if you just count from the syngas, these things are already 80% efficient LHV. They're quite cheap in capital cost. So there's a lot of talk, endless academic papers in Joule and whatever about really fancy ways to do this that may be better. But remember, they're better than something that's already 80% efficient and pretty cheap. So it's not clear to me why these advanced processes matter very much to me practically. They're cool, but I don't get it. So this shows you the whole chain. Very simply, if you want to make 1 gigajoule of fuel, this is showing you need about 2.25 gigajoules of electricity. And what I haven't said much about, but we've been doing a lot of thinking about, and I've been collaborating with a group at MIT about, is how to manage the intermittency of the solar. And the key thing is at the scales we're talking about, like over 100 megawatts of solar PV, diurnal storage of hydrogen is pretty cheap. And we've done the engineering on that really carefully. And so the way to think about it is you think about the solar hydrogen system and you demand a certain availability. And you do an optimization demanding an availability like 95 or 97.5%. That is 97.5% on an annual basis, using real weather data to look at variability. That's the way we think about it. Because just to be clear, we're running the air capture system and these other systems 724. We're not swinging that, just the electrolytic. So this makes it simpler. This is just making it into efficiencies. And you should, first of all, think this is a joke, right? 44% is terrible. Batteries have round-trip efficiencies of order 90%. So anywhere that batteries really work, they're going to win. But there are a lot of places where they just aren't going to work. And that's because, really most of all, because of the energy density. Innovation can make batteries cheaper. It can make the flow in and out better. But I think there are real limits to how much innovation can improve the core energy density of batteries in other constraints. Part of that, batteries are already using some of the most electronegative, electropositive, lightweight things, and lithium is going to invent new elements that are that are lighter than lithium and have a stronger chemical potential. And I think that is a sort of fundamental barrier. So my guess is that with solar getting so cheap, and another talk I said too cheap to meter, which is easy to beat me up for. Of course, it won't actually be too cheap for meter, but with solar getting really cheap, the idea that even if you have these kind of lousy efficiencies, and to be clear, this is efficiencies with really stock technology. We can do better than that. But with these efficiencies, there are going to be times where it really makes sense to do this, to use this intermittent solar to build in places where building costs are low and where you have excellent solar resource to make fuel, and then that fuel is easy to transport and store and sell around the world. And that, I think, is a general topic which is separate from the specific way I've talked about it. And just to give you a sense of the costs, don't worry, I'm not saying we can now make solar fuels at 27 cents a liter. But if you get solar PV to $10 a megawatt hour, which is definitely not true now, but I think doing that a little bit post-2030 seems pretty plausible to me in great sites, then the energy cost alone, not counting capital and operating, is something of order 27 cents a liter in this system. And there are two other things to notice. A lot of people worry about the fact, a lot of times I hear talk saying how energy intensive our air capture process is. Energy intensive is a relative number. You need dimension, right? And in this system, it's 17%. So yeah, we can make it better, but it's not that much of the total. And so it's not actually driving the process in important ways. So that's what I wanted to say about sort of giving you this idea there might be something important here in making fuels this way. And my view is that can be important for a bunch of the hard to decarbonize parts of the economy, like heavy transportation, shipping, aircraft, heavy trucks, and also some other parts of the economy which are really hard to decarbonize. So I think I could wrap soon, but I want to take 5 more minutes. I'm going to talk about order. Okay, so these aren't appearing in the direction I thought, but let me do it that way. So now let me step back. I'm just going to assume, I'm happy to ask questions, that all of you have some idea about what these core instruments are. But if you think of the climate problem like this, let me say for the first how I think about what these instruments do. So decarbonization is something that breaks the link between economic activity and carbon emissions of the economy. To me, it is absolutely the most important thing that we do. If we don't do that, we are just not serious about the climate problem. And there are all sorts of pathways, including one that I just showed you, to enable decarbonization. The central problem for decarbonization, in my view, is not in any way technical. While we may not right now have good technical pathways to go all the way to zero, we have good technical pathways to cut us beyond 50%. The big issue is the fundamental political reality, the street fight that luckily young people are now taking up, the street fight to win the political battle to start forcing decarbonization to happen. But we know methods to do it. Carbon removal can break the link between emissions and concentrations. In principle, perfectly, but all carbon removal methods, I think, will have significant costs and environmental impacts. And I think carbon removal is really thought of as something that we do to get that last bit of emissions or to go negative, but not as a substitute for decarbonization. Solar geoengineering can at best partially and imperfectly break the link between concentrations, the amount of CO2 in the atmosphere, and climate change, but only partially. And same for adaptation. Adaptation can partially, for some people, for some things, break the link between the physical climate changes and the human hazards. So how do they fit together over time? First, a few words about carbon removal. We often just give these lists of things as if they're all elements of one thing. I want to argue to you that there are really two categories of carbon removal that are sharply distinct, and that talking about them all as negative emissions is a mistake that fosters a kind of sloppy thinking that is environmentally dangerous. So I think there are really, one category are these things where the CO2 ends up in something that really is isolated for geologic time. That doesn't mean it's necessarily good, because a lot of these things might be very expensive or have high environmental impact. So I'm not saying this is good and this is bad, but these things here, I think you can truly call negative emissions, in the sense that if you fly across the world and put a ton of CO2 in the air and you want to remove the long-run environmental consequences of taking a ton of carbon from the geosphere and putting it in the active biosphere, then these things actually could do that with some cost and other environmental impact. Nothing up here does that. And I think the right name for these things is something else, like carbon banking or carbon reservoir management or delayed emissions. These are useful things. They might really be worth doing. But if you plant trees or do any of these other things that are basically just moving carbon between the atmosphere and the land biosphere, you're shifting between reservoirs that inherently are labile, that themselves change under climate change and under human action. And none of that can count as not doing the transfer of carbon from the geosphere to the active biosphere. And so I think we just need to start talking about these things really as different categories. And it's not good versus bad, because heck, delaying emissions half a century could be really good, but it's not the same as non-emission. So now on to talking about sort of how these things fit together over time. First of all, without any axes, but we now have a version of Nordhaus's DICE model that actually does this with numbers and in optimal climate policy. If you, as you all know, if CO2 emissions go on forever, then climate risk rises without bound. On that day where we have brought emissions to zero, and we will do it, and I am optimistic it could happen in my lifetime, where we bring net emissions to zero, we have, as I think you all know, not solved the problem. All we have done is stop the problem getting worse. And even though everybody's educated in this, should know that, you still get people really saying things that are clear they're not getting it, that they think that cutting emissions to zero means you solve the problem. It's not true. I think it is certain that carbon removal could be used, one of these methods, or a combination of these methods, to gradually pull concentrations back down. But I think this is inherently slow and mostly something we want to do after we brought emissions near zero. So in my opinion, solar geoengineering, which I'm not telling you much about, is something that if we use it, and I think we absolutely do not know now whether it makes sense environmentally or how it would be governed, but if we use it, if it makes sense to do it where you start doing it well before the peak, so you can ramp it up slowly, so you're going to shave the peak of climate risk, and then you ramp it down afterwards as you do carbon removal. So let's talk about how things look over time. That means that the start of solar geoengineering has to happen a long time before this day of net zero, and then it stops afterwards. So when does large-scale carbon removal start? Of course, some carbon removal has already started, but when does large-scale carbon removal start? My view is it starts when we've driven emissions down to maybe a third of their current value, or a little lower. And I think that's obviously before the peak, but not much before the peak. So what I'm saying is radical and maybe surprising to this audience, which my guess is more interested in carbon removal. And what I'm saying in simpler words than the last slide is the following. That if you ask most people the preference order, people will say that they prefer most of all emissions cuts, then maybe carbon removal, and then maybe we should talk about this awful thing called solar geoengineering. I'm not arguing with that preference order. Maybe it's correct. But it is wrong to infer from that preference order that that is the right time order. So what you get people saying, I think kind of glibly without thinking about it, is we should do emissions cuts, and then if they fail, then we should do carbon removal. But I'm not quite sure what fail means. This is really a political question. And then maybe solar geoengineering. That is, I think, really wrong. I think if you want to do solar geoengineering, it wants to, in the natural order of these things, due to the dynamics of carbon and radiative forcing, it wants to start earlier. And that has a profound implication. If we want to be able to make informed decisions about solar geoengineering, we need a serious international open access research program to understand better how it works and how it should be governed. And I haven't put dates on this, but if you think about the dates and you think about that peak, you want that research program to have started a decade or so ago, and really now. Thank you.
Thank you, David. And you can all see that this is the 30-minute version of the 30-hour lecture. There's so much in here to unpack, and we simply don't have time to do it. I'd invite you, though, to sit for a little bit with me. I'm going to talk with David for maybe 15, 20 minutes, and then we're going to open up the floor for questions and answers. We're very keen to get your inputs. For those of us who are joining from the live stream, again, my name is Julio Friedmann. I'm at the Center for Global Energy Policy, and we're here with David Keith. I want to start with something that's a little off axis from what you said. And it started actually with a comment that I heard from a professor here, a guy named Dr. Dan Steingart, who's an electrochemist. And he commented about the idea that we train engineers from day one that they should enter the world thinking about efficiency first. And that when you start with efficiency, then if you don't start with efficiency, you're leaving money on the table, you're running things wrong. And his point was the opposite. He said, maybe that's what we have done for good reasons, but we need to actually start training engineers to think about carbon limits, and that you may be willing to sacrifice efficiency as you go forward in the world in order to get a deeper carbon reduction. And it's sort of an interesting framing of this question. We have limits on resource, we have limits on capital, we have limits on atmospheric headroom for carbon dioxide. As we train people to go out in the world professionally, what should they do? How should we be thinking about these things?
It's interesting you say that we train engineers that way. I think of that more as the physicists who drift into this topic often think about efficiency the most. At University of Calgary, I was doing real engineering education, and I mean, efficiency, maybe we talk about it too much, but we talk to them a lot about process management and safety and design and teamwork, and I don't think we necessarily overdo it so much in practice, but I agree there is a way that people can over-focus on efficiency and not think about what I think tends to matter more in a process, which are the large-scale environmental and social consequences of whatever this process is and its costs. Because in the end, I mean, efficiency only matters if it's efficient use of something that really matters. But people, of course, we don't have an underlying problem of lack of energy. We have an underlying problem of too much, well, some people not having enough energy and energy being made in a way that has terrible environmental consequences.
Right. And in fact, the fact that we have pivoted from a world of energy scarcity to energy abundance is something that is just beginning to enter our consciousness in terms of how we think about politics and resource distribution and all these other kinds of things. It is not ubiquitous all the time. It is not universally true, but the rate limiting step is no longer access to energy per se. It's how do you get it, how do you use it? It's a different set of questions.
It's not clear to me that well, maybe it was more, but it's certainly true that I remember I gave a very early talk about air capture when it was much more, people disagreed much more strongly at ETH maybe 10 years ago, and there are people there who just said flatly that this process design is just bad and environmentally destructive because using that much natural gas is wrong because it could be better used to displace coal. And that is based on an underlying mental model that says there is a fixed and small quantity of natural gas that the world ever has, and that's all we can do under these constraints to manage the carbon problem, and that just seems like not the world we live in.
Right. And in 2009, there was still a plausible case to be made for that. And when I started at the Department of Energy working in the stuff, in 2003, the world was absolutely, we're running out of gas and we have to worry about it.
Not the world of people who were thoughtful.
Well, I recognize that.
Yeah,
I-
I don't buy that.
So I have to pause here for just a
Yeah.
second. Something I am in my own conversations with David, I have learned that he is incredibly precise about how he uses language, and I've had to improve my listening
but I mean,
as I go about it.
there was a lot of hype about peak oil, but I felt like I was living in an oil patch town. If you talk to the old people, if you talk to people who are deeply thoughtful, I don't think that at high oil prices, people talk peak oil. That's kind of the way the conversation goes. It'll happen again if oil prices are high, but that doesn't mean that there's a fundamental reason to believe it.
But I wasn't actually talking about peak oil. I was talking about what you said, which was small quantities of gas.
Yeah.
It was broadly understood that maybe we could get the hydrate someday,
Yeah,
but fundamentally, like cheap, accessible gas was really scarce. And of course, that changed radically between 2003 and 2010. And so now we have a world that's awash in low-cost natural gas, and that has helped displace coal. Now we have a world that is awash with abundant low-cost solar and wind in the right districts, and where the costs are continuing to fall. And that's really shaken up the whole gumball machine. It's made a lot of these things, but I still find that people are sort of hung up on this efficiency question. People are hung up on land use questions. How much, if we wanted to do this at some Goliath scale, we have to paper the earth with solar panels and do these things. And that always struck me as, again, you're sort of putting a false conceit out there for a false framing, like you're saying, if you do the stupid thing the stupid way, it's stupid. I want to sort of change that. If you're trying to think about the fact that we have a limited headroom for carbon, okay, and we have some specific set of needs to accomplish deep decarbonization. You talked a little bit about the staging order of these things. I keep coming across people who are like, we shut down the coal plants and we're done. And people are like, we shut down the gas plants and we're done. And it's like, I keep saying, no. And one of the things that comes back over and over again is heat. That we use heat in all kinds of ways. In some applications, you can make electric heat easily. In many applications, you can't. And so synthetic fuels are a way to think about these things. So how do you think about industrial demand, that whole world of applications in this limited headroom space?
I'm happy to answer that, and it's a good question, but I actually want to come back just one step.
Please.
So in terms of efficiency, I do feel like land use is a different category. So land is something where we actually do have a fixed amount of it, and where the land we take or disturb is land that we take or disturb from nature. So I think that the question of land use really is very important. So as we move to solve one of the great environmental problems, which is carbon, we shouldn't be creating others. And I think that's part of the basis for me taking very seriously solar, where you could do 20 terawatts on less than 1% of the global land area, or about that. And that's using real numbers of actual solar plants. People will publish these very theoretical numbers, but we've done observations. But that's something that's real for solar and for nuclear, but not for wind or biofuels or any of the others. And I think that really is the issue, that if you want to do that kind of scale, or even close to it with wind, and the ratio matters, you've got a huge environmental footprint in different ways on the land, and obviously same with biofuels. So I actually think the land footprint does matter, to me, quite a lot. But anyway, in terms of industrial, I think these fuels, although clearly you wouldn't go all the way to oil for most industrial, you go to gas, which you could do, or go to hydrogen. So I think that industrial can get managed by a combination of going to hydrogen or going to electricity, and then thinking about electric heat storage. So one interesting thing that gives you the gap between sort of theoretical and practical. So lots of people ask us, could the carbon engineering process be driven electrically? And of course, at the level of like a high-level box diagram or a paper, people are writing a bunch of these papers right now, it's easy. At the level of really doing it, which we've been struggling with inside carbon engineering, to actually make that kiln work electric, there's no doubt it's possible, and we've done some work. We have some test units, but it's actually not easy to switch these processes over. And when you start to think about it, there are really interesting things that come out. One of them is, in some cases, you can do high temperature electric storage that allows you to manage intermittency. So I guess, answering a different way, I think people in thinking about this keep imagining that the grid will manage the intermittency, and that they can just think about this low carbon. But I think the crucial thing is that unless nuclear really makes a comeback, if the dominant low carbon energy is solar, then applications that can do a better job managing intermittency do better. And everybody would prefer not to have intermittency, but it's the reality. And so I think there's a huge premium in developing these industrial scale things on thinking of things where the intermittency is less painful. So that may mean, for example, adding some thermal energy storage to your system, high temperature storage.
One of the things that's been very exciting for me is to see the maturation of policy in this whole landscape, of maturation of policy around direct air capture, around CO2 removal, around synthetic fuels, around CO2 utilization, around carbon capture and storage. When I first met you, none of this was on the board, and now we actually have laws that allow you to make money, that govern the processes. Can you talk about how those policy shifts are affecting the thinking of your companies and your thinking as a scholar?
So the carbon engineering's ability, we've raised over $100 million. There's no question that's been fundamentally driven most of all by California low carbon fuel standards. So from the beginning, when we were raising the first $3 million and with just me running it, that was the big thing we kept holding up, was LCFS. And now, fast forward to now, where we have partnerships with, Oxy Petroleum. It's a major investor, no controlling interest or special powers, but they're a big investor. They clearly are thinking about a combination of the Q45 and the LCFS system, enabling either pure storage or enhanced oil recovery to really make this economic now. So the point is, people will often say that there's no existing policy, and I still see that, and I think, well, we see policy on the books that we're trying to bank finance against. So that is absolutely crucial to doing this. And I think one of the larger lessons is when you want to promote the development of technologies like this, I think setting up local demand pull by high local prices is much more powerful in really driving the kind of large-scale change than kind of R&D push.
I was actually going to come to that. Our center does a lot of scholarship on policy in many different kinds. One of our scholars, Noah Kaufman, does a lot of work on carbon taxes, and he and I go back and forth about what's the appropriate role for a carbon price or a carbon tax versus procurement authorities versus subsidies versus tax breaks versus all these other kinds of policy options that one could exercise at a different scale in a different context. What's the political viability of these things, et cetera, et cetera. Just thinking about the next 5-10 years, I want to focus in on the short time scale for this question and the next one. What policies would be most material, you think, in getting stuff to market? How do you jumpstart the economy from a policy perspective?
So I have a particular policy design that I like that was developed actually in some Alberta CCS panel that I served on with a bunch of CEOs. And it's the following. It's that you offer fixed and high prices for a limited quantity of things, in particular ways that you're doing carbon removal. So you offer a fixed high price, but for a fixed total quantity. So you say the price is going to be for some particular thing, $200 a ton carbon for the first 10 megatons, let's say. And after that, it steps down. And a system like that allows the government to have certainty about the total cost that they could be on the hook for, because it's the integral under the curve. But it allows the companies to have price certainty and this very clear competitive environment. So they have some price certainty because it's not a market. They can point to that number and potentially bank finance against it. But if we're two companies competing under that, and there's, let's say, 10 megatons total, and we're both kind of building megaton-a-year plants, we know that there's that gravy, that high-cost gravy we want to get early, and so there's a competition to get moving fast.
Right.
But it's a competition that doesn't require government to play the role of a beauty pageant picker, it has all the behind-the-scenes crony capitalism, because it's a very simple rule. And it doesn't mean that you have to award some big prizes or special things with special companies. And I think that stuff inevitably is hard to manage and bureaucratic. So I really like schemes like that. And I think that we need to think about them in specific areas of technology, among them this one, to try and pull important technologies out of the woodwork.
It's interesting that you posit this, because we've got David Hawkins here from NRDC is in the audience. That was tried under Waxman-Markey specifically for carbon capture and storage, and there was exactly that kind of system proposed, which unfortunately was not enacted. But thank you for sharing that. I'm going to ask this question, the next one, and then we're going to go to the audience. We're going to try to be brief. You mentioned Oxy as an investor. One of the questions that I grapple with myself, and I find it's very hard for audiences to think clearly about, is what is the near-term role for oil and gas companies in all of this? What would you ask them to do? What should we expect them to do? We're very good at telling them what not to do, but we haven't given them an idea of what's a good use of their time and money. How do you think about that problem?
Well, I think the most important things for oil and gas companies to do is not to oppose actions to do deep decarbonization. And I think the reality is some of that is still happening, and it's just the common sense reality of interest. If you really do deep decarbonization fast, policies that I would like to see, the oil and gas industry gets hammered really hard, which is the right answer. And I think that's obviously not an answer they want. People have interests and they're fighting. And I think that's the really hard part. At the same time, there are technologies that those companies have and expertise they have that can be part of decarbonization. But I think as firms, it's going to be difficult. So one of the reasons that I'm very excited about working with Oxy is we're working with Oxy at the level of a new top-level business unit, Oxy Low Carbon Ventures, whose sole job is doing us and a bunch of other things like us that are low carbon. And if you run that in the future, and I know this is on a public web stream, and just think it through, if in a world where there are really strong carbon constraints like I as a citizen would like, something like Oxy Low Carbon Ventures will keep doing better because it's in a low carbon world, it'll compete well, and regular Oxy will not do so well, and their interests will start to be opposed. That's the reality. Mm-hmm. And then institutional investors will come and say, we'd like pure plays. That's what the big institutional investors do. They say, we'd like to be able to invest in clean tech or in brown tech, and we want to make the choices, not you. That's what they did to BP and others. And then there will be pressure to break them in half. And I think that's fine. And I think, in the world that I want to see, what I care about is the people and the expertise. But my sense is that the really large existing oil companies mostly will not survive this transition. Because in general, when you have these big transitions, the legacy they bring is not legacy that's really useful in doing the competition. There are people in them and expertise and individual companies and capital, all of which will be useful in transition. But the big packages, the idea that they can just kind of transition to a green world, I kind of doubt it.
One question before we go to the audience on solar radiation management. Thank you for the explanation. You did a lot of the questions I was going to ask, you've already answered. But we have here at Columbia the Sabin Law Center that Mike Gerard runs. And when I talked to him about CO2 removal and carbon capture and storage, he's like, hey, the legal issues here are not a big deal. When I talked to him about climate engineering, he's like, they're incalculable. We are just have not really started as an enterprise around the kind of legal and governance questions that matter in a world in which solar radiation management works. And again, you brought the idea forward about the question of staging. How should we be thinking about beginning real work on governance and legal questions around solar radiation management?
Well, so the central questions around solar geoengineering, in my view, are about governance. Governance, it's so cheap already that the cheapness is, if anything, more a bug than a feature, because the cheapness could incent unilateral action. So we do not need capitalistic competition to make it cheaper. The challenge is to develop a larger and more shared, it'll never be perfect, understanding of what the risks are, and that I think is best done by public institutions of different kinds or NGOs operating as transparently as possible, that are as inclusive as is reasonably possible. I think that's how you develop some trust in uncertainty and knowledge about a thing like this. And I think we need to begin the governance discussions early, and I think there's more happening than some of you may realize. So János Pastor, who was formerly the chief advisor to Ban Ki-moon for climate, so a person at the center of the climate policy axis, he is now running an effort on solar geoengineering governance, an NGO, that has amazing access up to near or sometimes at the head of state level globally. And that job of that NGO is not to promote or retard solar geoengineering, but to promote international discussions about its governance.
So this is C2G2.
C2G. And that is happening. So there are increasingly serious conversations, that I've certainly been party to some of them, between governments, and I think the beginning of a pathway that might lead, for example, to a UNGA resolution of some kind. I think the central thing many, but not all people agree, is that we need some kind of restraint on unilateral action. It may or may not be a moratorium, but looks like it. And I also think I'm very excited about trying to support and encourage smaller democracies to play a big role here. I think we're sitting in the U.S. and the U.S. audience, but the U.S. is not, nor the U.S. nor China are necessarily very well trusted around the world, and I think are not very likely to be the countries that do this.
I'm shocked to hear
and
you say that.
And I think that, and with a particular technology like this, where cost is not the issue, I think there are a lot of scenarios where a set of smaller democracies are actually the ones that drive the outcome.
Again, I could do this all day, but I really would much prefer to hear from you all. We've got a microphone going on. First, the woman in the back here with the Dayglow shirt.
Good morning.
If you'd please introduce yourself.
Yes. Good morning, Elizabeth Halliday, the Clean Capitalist Leadership Council. Thank you very much for being here. I enjoyed your remarks. The lever, my particular organization is trying to push or pull is private tax-exempt debt to get the capital moving to these new types of innovation. Today also is the deadline on the House Select Committee for the climate crisis, and I would encourage anyone in the office to try to make their wishes known to help the elected officials know your policy views. In terms of your particular technology, how would you see this being deployed in the market? Would it be for a particular industrial process, or would it serve the larger grid? How would you see this rolling out in the marketplace?
I mean, carbon engineering is direct air capture technology. So I think in the near term, we're in the middle of trying to develop 2 or 3 different plants, because that's what you do as a small company. So you've got to put together an offtake agreement, an EPC, and land, and so on. So one in Canada we're thinking about more as a fuels play, and a U.S. one as a combination of pure sequestration and EOR. And who knows which of those will move forward, but they both look pretty promising. So that's sort of in terms of plant one. And the U.S. one, we're aiming at 1 million tons a year. So that's order $1 billion of financing we need. And I'd say it is looking pretty exciting. And a lot of the levers are coming together much better than I would have guessed, courtesy of this great management team. It's way beyond my expertise to manage a project like that. I think you can easily see a bunch of plants being built for some combination of pure storage and EOR. And what I think we're seeing is there are interests from some surprisingly big corporate players in pure EOR, in pure storage. And it's not exactly clear what's driving them, and I can't tell you which ones it is, because we don't, these aren't public yet, but there are clearly players out there, A-list corporates, that would like to make deals to have like a 100,000 tons a year class or more of pure certified storage from the air. So that's really interesting development. I think this fuel stuff that I talked about here, I take very seriously. I think that it's something that could grow, to be 10 million barrels a day in the 2030s, but I don't think it starts. I think it starts piece by piece. I think it's smaller, because the fact is it does depend on solar and it depends on the markets getting stronger, more things like low carbon fuel standard, and it depends on the electrolysis technologies and solar just getting a little cheaper. So I don't think it makes sense to do a giant one of those now, but I think it's really important that that's recognized a pathway, and we begin to develop the financing and business models that could allow you to build these really big installations of solar in good locations and use it to make something like this.
Just as an addendum to that, one of the things we're exploring at the center is the ability for either states or cities or institutions like ports to actually begin procuring directly these low carbon fuels as a way to start getting some of that into the market. Next up here, and then we're going to get you, and then you, and then you.
Thanks. Dave Hawkins with Natural Resources Defense Council. A comment and a question. The comment is one of the important takeaways for me from your talk, David, is not to confuse the issue of preference for the reliance on techniques with the timing of sequence of activities. I think that's a very important concept that all of us should take away. I agree with your analysis about we'd like to rely least on something like solar radiation management, and it may turn out that we don't want to rely on it at all.
Yep.
But that doesn't translate into not thinking about it and not doing the research. My question is kind of in the weeds, but you, in your talk, described a value of about 10 tons per square meter of contact surface, if I recall. But on one of your slides, you had 20 tons per square meter in describing the carbon engineering. Was that a description of what you hope to achieve with your technology, what you've already demonstrated, or something else?
Good question. So first of all, one minor thing, it's not per contact surface. So inside the corrugated contactor material, there's, this is why I haven't talked this for a while, I'll get the numbers wrong. There's at least an order of magnitude more surface area behind. So I was talking about per square meter of inlet of the main contactor structure, which has behind it the packing. And we can achieve, I don't know the upper bound, but by running fans hard, we could achieve more than 20 easily. It's this trade-off of capital and operating. And that's in that, I mean, that's stuff that actually is not at all really a trade secret. A bunch of that you can get in that, not the Joule paper, but that earlier paper we published that has all the trade-offs. You just kind of put the numbers in, you get the trade-offs. So there's nothing magic about that ton. And yeah, you're right, I was inconsistent. If the slide says 20, I'm mixing it up. But you get numbers about like that. You can get them higher, but it's that kind of number you get. And what's interesting is the people with very different, Climeworks isn't very far from that because it comes to be the same. I mean, again, you don't want the fan to go too high because then you both have, you have more pressure drop and energy costs in the fan. There turn out to be a bunch of trade-offs that just bring you back down to a thing like that.
Yes.
Hi, Ben Hogan from Inherent Group. I'm an impact investor. On the topic of carbon policy, has there been any discussion about a mandate similar to the Renewable Portfolio Standard for renewable energy by states to kind of mandate the purchase of carbon sequestration?
So I think Julio would know better whether that's happened, but my view would be I'm not sure I'd be for it. I think we can make something more general, like low carbon fuel standard. The essence of, there's a lot of complexity. The essence of low carbon fuel standard says you're free to sell any fuel you like in California that ends up in transportation, so long as the average energy intensity per unit of energy per megajoule delivered to the vehicle's drive shaft, that average is less than X. And what's really clever about that is in principle that applies to electric vehicles as well. It's a clear standard that is technology neutral, that focuses on the thing that we care about, or one of the things we care about. We care about pollution and other things as well, but for climate. And it doesn't have government setting the price, but it allows this sort of trading, and it allows new things to come. Part of the reason my company was able to get where we got is that people weren't, when we started, thinking about air capture or giving us any incentive at all. It wasn't the flavor of the month. But because LCFS was written in that general way, we were able to say that could apply to us, even if the people who wrote it weren't thinking about this at all. And we could get that money. Now, DAC is a big thing. People like it. So I would kind of resist the idea that we write really fine little regulations saying, oh, we want this from CCS. Well, in some cases, CCS may not be as good as lots of other things we might do. And I think in general, we shouldn't be that kind of technology forcing.
Right. So philosophically, I agree. Let me take a moment to answer this because I do know something about this. The thing we should be focusing on is carbon. We should be as technology agnostic as possible. And the good news is that now about 9 states have actually mandated that. They have said for power production, we're going to go to 100% zero carbon. And that allows nuclear or CCS or anything else to compete. Also, in every case that I know about, they've done something smart, which is they say, we're going to let the agencies that know things about stuff define what zero carbon means. Because zero doesn't necessarily actually mean zero. It might be 50 kilograms per megawatt hour or something like that. They're waiting to define what these things mean. But they've opened both the ambition and the political aperture by doing that. They've allowed you to have a higher environmental standard and get more players on the field, which is going to reduce cost and reduce risk and make local successes in local markets. There's a question about doing the same thing at the US level. There's a draft bill, the Smith-Lujan bill, to create a clean power standard for the entire nation. And what's interesting is in that draft bill, they say direct air capture is a compliance mechanism. If, in fact, you can't get to zero, you can undo some emissions through direct air capture. The last thing I'd say is it's the same question that you asked about power you should be asking about everything. You should be asking, what should we change the renewable fuel standard in the U.S., which is an ethanol standard? Should we make that a low carbon fuel standard and increase ambition and increase aperture doing so?
Yes.
That's a much harder political lift. That is not a simple thing to do. But it's fair to start asking, isn't that what we should be thinking about and how we should be thinking about it? You had a question, and then you over there. We'll do our best, folks. We try to get as many as we can.
Yeah, hi, Jonathan Ratner from the New Jersey Economic Development Authority. Earlier in your talk, when you were speaking about big categories of carbon-free power generation that you thought had real legs on an overall cost, and considering other externalities, other impacts, it was a list of two. I thought I heard: solar voltaics, photovoltaics, and nuclear. Could you speak a little more about what's behind your thinking of leaving wind off of that list, breaking out between offshore and onshore, if you think there's distinctions to be made there, and maybe speak a little bit more practically about the issues you see with nuclear continuing to be in the mix the way you see it. Thanks.
Well, the nuclear question is so hard. There's so many problems. It's hard to know where to start, and it's very hard to know what are the next steps that could make nuclear a useful part of things. But just in terms of inherent environmental impacts and footprints of technologies, I think here's some things you can say. So hydro, for example, has a kind of hard limit of just a few terawatts, and the power per unit area is under a watt per square meter, and tends to have very big environmental impacts in relative terms. That's, I think, just a kind of a hard reality. Biofuels, you're typically significantly under a watt per square meter, and let me be really nerdy for a minute. There's 150 10 to the 12 square meters. That's 10 to the 12, and terawatts are 10 to the 12. So it's pretty easy to do the math here. So if humans need, if you want some of the poor people in the world to have access to clean energy, you want total energy use, I think, to go up, but we need carbon emissions to go down to zero. So you need to have something, over 20 terawatts, maybe over 30 of clean energy, of low carbon energy pretty quickly. So then I think you start to think about which things are likely to have a big footprint. So in my view, solar, which real solar plants, not theory, can get you sort of 10 watts per square meter. And so do the math, you find that's like all human energy use at a couple percent of global land surface. And that's something we can, there's real impacts, but we can manage that fine. Nuclear has even smaller land footprint, lots of other problems, but wind, the actual measured observed, we published a paper with an error that we fixed, but the error was like 30%, 27%. The actual observed energy density of wind farms, not counting under the turbine foot, but of wind farms, is well under a watt per square meter, and that's for really good wind farms. I think it really goes down to more like half a watt per square meter, and that says you really are covering. I mean, you want half a terawatt out of the U.S., you're covering a big fraction of the U.S. And that has impacts. It has impacts in all sorts of ways, in the roads and service and so on, and it changes the climate. And that was a radical thing when we first wrote it, but there's now like 100 papers. Just last week there was another paper from a Chinese group showing this. We have satellite data now. There's 10 studies showing climate changes from wind turbines. To me, that does not mean that we don't do wind, but it means that we think about it, and I think there's lots of ways that wind makes sense. There's not a black or white thing, but I think you don't think about building wind up into the giant thing, because the impacts start to really creep up.
Right, and this is one of these questions where so people are so fast to forge an axis of contention where one doesn't exist. It's like you can say what you just said.
As soon as I published this, people wanted me to testify against wind turbines, which I've never done. And to be clear, if it's a choice between coal and wind, of course wind should win.
Right.
But the issue is if we're really talking about moving towards a clean energy future, and we want to manage other environmental impacts, I think my summary of that work on wind power's impacts is, I think we should push the scale towards things that have a lower environmental footprint.
No, we do not have time for follow-ups for anybody. Sorry. You've been very patient in the pink shirt there. And you've also been very patient. We'll get you next.
Hi, I'm Sue Dorward. I am a carbon tech graduate student here. And I was really surprised about your comments about the oil and gas industry. I mean, given carbon engineering's deal with Oxy and
My CEO doesn't like me saying it, but it's my duty to say what I believe.
Okay. So I'm wondering what your thoughts are on carbon negative EOR and the use of oil and gas industry expertise for geological sequestration.
Obviously, we need their expertise for geological stations. Of course, I worked on CCS for 10 years. Of course, we need their expertise for geological sequestration. But that expertise is in people. The question is if people and in subsidiaries, the question is under real climate policy, the interests of the people putting together sequestration plants are going to start to be opposed to the interests of the people running the big companies. And I think they will inevitably fracture. And I think that's healthy.
In the back there.
Thank you. So thank you for the presentation. I'm Maria Paola Sutto. I work here at Columbia University in the Earth Institute in a small unit, innovative unit, the Urban Design Lab. And what I want to ask you is a two-pronged question. The first, flatly, is given the richness of the energy option, what is it your wish for 20 years from now? So this is purely speculative, okay? And the other is this instead. I see that you talk about, the policy, the government, there is the industry, the innovation, and then there is the civil society. So I always see 3 points, and point were connected, this triangle. So we could do things to accelerate the consumer desirability, fashionability of something with a tool who can be studied for this. These days, I'm very fond of the toolbox. We produce toolbox in our infrastructure study. Okay, so do you think that something like this could be desirable?
I'm not sure I fully understood the question, but I guess if you're asking, so I don't have a fixed idea about what happens in 20 years. I think people's ability to predict energy futures is really lousy. I think that the central thing, I am very excited about the rise of the youth movement, and I am very frustrated with me and my peers and the level of hypocrisy around climate. I've spent too much of my life in rooms where people happily talk about doing something, where people make grand pronouncements and nothing happens. And I think I think maybe the world spent a little too much time, and some people in the environmental community, putting their kind of hard-won political capital chips on trying to get something through a framework convention. I do think we need the framework convention, but I think we have to admit in the end this is a country-by-country brutal political street fight. And we have to engage in that fight hard. Because if you want to cut emissions at the pace we need to, we're talking about several percent of GDP. And in a democracy, that only happens, in my view, if a government gets elected with that as a central plank. It's the only way you have legitimacy to do it. It can't be an inside the beltway deal. And for that to happen, you need some significant fraction, not 50%, like a third, that's typical in democracies, who have this as their number one thing. It's not having 70% of people kind of care about climate, that doesn't get a deal done. And I am at least somewhat happy about what just happened in Canada, where surprisingly, climate was polling in the election, which normally polls, if you just ask people a free question of what they care about, typically climate is like 10th. It rose to number 2, second only to healthcare, and in many senses, it was the core of what the final election battle was fought on, and the sides that won in action won. And that was the first election like that in a kind of post-youth movement, Fridays for Future Western democracy, and it was pretty exciting. But I think it's a long way to go, and I'm personally, been involved in climate for 30 years. My level of frustration is really high, and I think we need to find different political ways to do this. And I don't know what they are. I think it's something mostly for young people to figure out. But it needs a level of political action that is really different from what we've seen before, or we will not get the job done.
Right, so we still have lots of questions. We've only got 10 more minutes. I'm going to go first of all to the question in the far back there. Then I'm going to take a question from Twitter, and then we've got a student up front who's also been very patient. We're going to, and then see where we're at. Go ahead.
Hello, Christoph Meinrinken, Earth Institute. I have two totally separate questions. The one...
Please be brief.
Yes, first one is on your slide with the red numbers. I think I heard you say that you would run the hydrogen process electrolysis intermittently, but the DAC 24/7. What are the trade-offs in terms of not running it or using storage for that? And the second, totally different question, why would you not consider planting lots of trees over the next 50 to 100 years, a carbon negative technology, quote unquote? Or maybe.
Let me ask that latter one. I think it's really simple. So I think planting trees in lots of places is something really worth doing for all sorts of good reasons. But it can't count as the negative of burning geologic carbon, because if you built those trees, either human choices in the future, people can choose to do something else, we can't bind the future's hands, or climate change can make that carbon come back out of the trees. And in particular, the ways that planting trees can buy you much less risk reduction than you thought, for two reasons. One is you build all the trees, plant the trees, and if the climate warms up a lot, then that carbon is more likely to come out and you've actually not decreased the risk at all, A. And B, in lots of latitudes, you plant trees and they're dark. So you don't get as much benefit as you thought because the albedo offsets it partly. So I am not against planting trees, but I think that the idea that it counts as just as if you didn't emit the carbon does not pass Earth Science 101. And I think the level of overhype around it is really high. And also, people understate the extent to which, at least for me, I want natural forests. And natural forests burn and have forest succession and have open places and closed places. And we could manipulate some of the forests to have a lot more carbon, but that is not environmentally free. It has real environmental consequences in those forests. And so the idea that kind of, it's easy in an urban environment, if you don't spend much time in forests, just think like more carbon is more natural. That's not true.
Just a quick fact that might help this discussion. Last year, California reduced its emissions economy-wide by 5 million tons of CO2, and the fires emitted 35 million tons of CO2. It's just got to be part of the understanding of this kind of math. I'm going to take a Twitter question, and then we're going to go to a student up front. Twitter question came from Keith Leahy of Duke Energy, and he asked, does Dr. Keith have a view on the recently published paper in Science making a claim that degrowth should be preferred as a climate mitigation measure? Sort of a Václav Smil kind of sensibility.
Degrowth meaning making the economy smaller.
Yeah.
That's a hard one. I think that it is certainly true that those of us who are privileged to live in the richest tiny fraction of the world, our happiness is saturated and more consumption is not buying us happiness. And that it is credible to talk to the richest about ways that we reduce the footprint a little bit. But I think that's a hard and long conversation, because that kind of social change to me is the kind of social change like the social change between men and women's place in society, or any other social changes that tend to happen over more like chunks of a century. And then we have billions of people with really inadequate access to energy who I think we should think about a future where they have more access. So I just don't see that really reduces total energy use.
Thank you. Let's take this one up front. We still have probably time for one or two more questions. So I see a couple of you. Go ahead.
Hi there, Zach Byram, current CPAS Master's student in the Environmental Science and Policy program. So EOR is often used as a vehicle to get the cost of sequestration down. As I understand, EOR is about 4% of oil extraction, or used for about 4% of it. I don't know if it's the US or globally, it's just a number I've heard.
That's US.
Sorry?
US.
US. Yeah. And one estimate I've heard is that it'll probably peak at about 8%, after which some estimate, I think there's one DOE estimate that said that just commercial sequestration without EOR would just overtake it. After that 8%-ish point, what does commercialized sequestration look like without EOR?
Well, if you're talking sequestration from power plants, I think sequestration looks like putting the CO2 underground, driven by a carbon constraint. And I do think you have to worry if you've put the money and regulatory force into getting a power plant to capture the CO2 and put it underground. If you're doing EOR, you are, all else equal, slightly lowering the you're increasing oil supply and there's some elasticity, but you can't count all of that CO2 as being, it's all that actual CO2 is sequestered, but there's a consequence and a consequential LCA of some extra carbon coming out. You got to think about what that is. So I do think that if you think purely about the fuel side, which I talked about, the cheapest way right now to use DAC technology to make fuels that have the that are fuels that are carbon neutral is to do EOR. And you can do EOR with DAC, where you really have the same amount of carbon truly coming from the atmosphere down the well as coming up. So you can really make fuels which in a real, honest, no-nonsense life cycle really are carbon neutral if you want, or even carbon negative. And that would beat the process I showed you in the short term, for sure. I think in the long term, I expect that the process I showed you will eventually win.
In that exact context, the heterogeneity among oil companies thinking about this is enormous. And I'm just going to give you one position on this, which is from the CEO of Occidental Petroleum, Vicki Holleb, and she said we should think about the last barrel of oil in the world is produced through EOR, that you want it to be a carbon neutral fuel to the end.
But to be clear, to be a carbon neutral fuel in the way, I mean, if you think carefully about consequential LCA, I think that CO2 needs to come from the atmosphere.
Right.
So I think it really is different if the EOR is just from some other CO2 you had for a different purpose. I mean, clearly, if the EOR is from CO2 you produced from a CO2 well, which is what most EOR is now, there's no version of that that counts as carbon neutral.
Right. So we probably only have time for one more. Let's take this person here. I see you guys in the back. We'll see if we can get to you.
Hello, my name is Amy Larkin. I'm the author of Environmental Debt, The Hidden Costs of a Changing Global Economy. And I want to ask you, a lot of what you talked about is almost linear in how you're presenting it. I'm sure that's not how you're thinking about it. But given the fact that I have the paper today, every day we see the world is falling apart around us. The impacts of climate it's not linear. It's insane. And how do you think, or do you think it's possible to protect us from the deployment of solar geoengineering in an emergency situation, which feels like it's coming sooner and sooner? I'd be curious how you feel about the emergency piece of the story.
I see why people want to call climate an emergency, and I think there are some senses in which it's the right way to think about it, given the almost total lack of serious action and the way that it's a cumulative problem. I think there are ways in which emergency is a useful word, but I do think that there's ways in which the hard truth is it just isn't an emergency. That's why we're not making progress. So I think if there really was an asteroid inbound, I don't think human societies would have much trouble figuring out how to cooperate to meet that threat. And I think the challenge of climate is it is a slow cumulative thing where it increases the frequency of all sorts of events, but not in a way that has really sharp thresholds. And most of the damage is far in the future. And that's why it's been so hard to get action. And that's why the fundamental challenge is something at some intersection of moral and political, of figuring out how we get the level of political commitment we need to take real steps now that fundamentally are mostly to benefit the future. And I think it's tempting to say that the climate crisis is so acute now that we must act or we're doomed. If that was really true, we'd be acting. The problem is it's not quite true, but we should act because it's the right thing to do, and because not doing it passes something awful onto our children.
Right. So there's an awful lot more that we could discuss, and I would love to have the opportunity to discuss, but I feel very, very fortunate to have thought a little bit about these very, very complex and ornate topics with someone as extraordinary and clear in his thinking and his speaking and his presentations as Dr. Keith. Please join me in thanking him.
Thanks very much. Thank you.